Scientific measurements. When scientists record a measurement, we do so in a very particular way, so that every digit that we write down, we are certain of, except for the last digit, which is estimated. So, thinking about the carbon monoxide pollutant, they're measuring things like this. So here are two different tables measuring carbon monoxide concentration in parts per million every 5 years. So 1990, 8.9 parts per million. In this table, it says 9 parts per million. The way a scientist understands these numbers is 8.9, we're certain of the 8, the 9 is an estimate. And generally, we assume plus or minus 1 in the estimated digit. So this would be somewhere between 8.8 and 9.0. Over here, recording 9 parts per million, the 9 itself is an estimate, and we're talking about between 8 and 10. That's a much larger spread. This one, 3.1 or 3. This, to a scientist, means between 2 and 4. This means between 3.0 and 3.2, a much tighter measurement. So all of the digits are certain except for the last one, which is estimated. And it's important to have that estimated digit. If there's only one digit, that digit is estimated. So how many digits get recorded depends on the measuring device. So this is very important. Scientists always read between the lines. So if we look at this balance, there's 0 grams. We're going to ignore the ounces side because that's English. And we're scientists, we're going to use the metric system. So this big line is 0, and this one is 10. And then we look at the little lines in between. There's 10 lines in between, which tells us each of the smaller lines is equal to 1 gram. So when we look at this mass, we see, this red line here is the one that's going up and down with the balance. We see that it is definitely more than 1 gram, but less than 2 grams. So we're not just going to say 1 gram, because that would imply we're guessing that it's between 0 and 2 grams. We know, we are certain it is at least 1 gram. So we're going to record 1 gram as a certain digit. So 1, and then we're going to read between the lines. We're going to estimate. I should have made this illustration bigger. But we're going to look between this 1 gram and 2 grams, and we're going to imagine 10 divisions. It's very tiny, but you can kind of picture half. Well, it's definitely less than half. And so you might think, well, maybe it's a third of the way, maybe it's 0.3. So you might write down 1.3 grams. Someone else might write down 1.2 grams. That's okay, because there's uncertainty in that digit. We have information. We know it's not 0.9. It's an estimate, but the estimate is very, very important. So the way that you know how many decimal places to put, and I'm really going to get on you about this in lab, is you estimate 1 decimal place past the smallest division. So here, the smallest lines represent 1 gram. That means we're going to estimate the next place. If you have smallest divisions being 0.1 centimeters, you're going to estimate the next decimal place. 1 degree Celsius on a thermometer, you estimate the next one. This is for analog devices, things that are not digital. If we have a digital device, like we use digital balances, that takes care of it for you. You write down everything, and the last digit is uncertain. So let's look at these two. Here's a thermometer. The end of the red is right in here. and we're supposed to record the measurement to the correct number of digits. Well, this is 100, this is 110. So what does each of these small lines represent? 1 degree, right? So this is 100, 101, 102, 3, 4, 5, you get the idea. So each line is 1 degree, so that means we estimate tenths. So where does this line fall? It looks like it's between the 3 and the 4, right? It's definitely bigger than 103 and less than 104. 103. We are certain that it is between 103 and 104. The estimating is the next digit. So what do you think that is? What do you want to call that? Point 2? Okay. I might call it 0.4, but it's okay to have some variation there. It's uncertain. And the unit, what do you suppose the unit is on this thermometer? Fahrenheit. No. Celsius. It's not going to be Fahrenheit because this is science. We don't use Fahrenheit thermometers. It's probably not Kelvin because 100 Kelvin is crazy cold. So it's probably Celsius. I've never actually seen a thermometer that was marked in kelvins because the conversion is so easy. Any questions about that one? Let's look at this. This is a volume of liquid in a graduated cylinder. And it looks like there's almost a contact lens floating on top, doesn't it? That's called the meniscus. And that's an effect of surface tension and absorption onto the walls and all this good stuff we'll talk about later. When we measure a liquid, it's going to have a meniscus, and we always measure to the bottom of the meniscus, which is going to be in the center. So we're measuring right down here, and then let's look at these markings. This is 4, and that's 5, and there's 10 divisions in between. What does each line represent? 0.1, a tenth of the unit on here. I'll just tell you, the unit on here is milliliters. So this is a tenth. So here we've got 4, this is 4.5. We can all agree that this is more than 4.5 and less than 4.6. So we are certain of the 4, it's 4.5 something. We are certain. Then we have to estimate the next one. So what do you think? 8. So 4.58, and then the unit. Any questions? This is a really, really important skill. Significant figures. You guys heard of significant figures before, I hope? It's okay if you don't like them, but hopefully you've all heard of them. I'm going to go through this fairly quickly, and we're going to get some practice in lab today. So the precision of an instrument, of a measurement, depends on what instrument you use. We need to preserve the amount of precision when we do calculations. And there are different ways to do this. The most rigorous uses differential calculus. Anybody want to do that instead of sig figs? I don't. I learned it in college and promptly forgot it because sig figs are so much easier. So significant figures or significant digits give a lot of students trouble, but once you understand them, it's very easy to remember. And so if you struggle with sig figs, please work with me and we'll get you straightened out and it'll help you the rest of the semester. So what we refer to as significant figures are the non-place-holding digits in a recorded measurement. They include all of the certain digits and the first estimated digit. So first we need to learn how to count sig figs. The more significant figures a measurement has, the more certainty we have in the measurement. So when we count sig figs, we use these rules. And these are in your book. All non-zero digits are significant. So if it's not a 0, it's a significant figure. That's easy. So in these examples here, these are examples of non-zero digits. Like, we really need non-zero? But anyway. The 1, the 3, the 3, and the 1. That's a 0. We'll treat zeros in a minute. 4, 2, and 1. So no questions about that. The only confusing thing is the zeros. There are 3 kinds of zeros. There are zeros on the inside of the number. Your book calls them interior zeros. See this 0? It's trapped between non-zero digits. These zeros are trapped between non-zero digits. Those are always counted. Always counted. Then there's zeros that come at the beginning of a number. They lead the number. Leading zeros are not significant. They only serve to locate the decimal point. So 0.00023. These zeros come at the beginning of a number. All they do is hold the decimal point. They're not really part of a measurement, and so they're not counted as significant figures. 0.04268, again, leading zeros. You're going to see these in numbers that are less than 1. Because if I say, I have 4.5 pounds of grapes, I'm not going to write 0.4 pounds, right? This is dumb. Why write those zeros in front? They are not needed. They're not needed to hold the decimal point. They're just not needed at all, so we don't write them. These zeros are just as meaningless as these in terms of measurement, but we need them to hold the decimal point. So we don't count them, but they're important. And then we have the trailing zeros. So what I'm telling you here is slightly different than what your textbook says. It has the same outcome. If the textbook explanation makes more sense to you, great, use it. I find that my explanation it obviously makes more sense to me, but it also makes more sense to most of my students. So the trailing zeros, these are the ones that come at the end. Trailing zeros are significant if there's a decimal point written in the number. It doesn't matter if the zeros are before or after the decimal point, but there's a decimal point here, 120.00. There's a decimal point. That means that all of the trailing zeros are significant. 39.0, there's a decimal point. 1.432000, there's a decimal point. These trailing zeros are not holding a decimal point. They are there because they reflect measurement. If there's a decimal point anywhere in the number, the zeros at the end are significant. The zeros at the beginning, never significant. Trailing zeros before an implied decimal point, so the number 300, does it have a written decimal point? No. There's an implied decimal point. We know that the decimal point would go right there, but it's not written down. Trailing zeros before an implied decimal point are ambiguous. They should be avoided. Okay, we're going to avoid them. If they do crop up, we're going to assume the worst, and we're going to assume that they are not significant. So 100,000, 238,100. You think about, I haven't read this sign recently because I just kind of drive here on autopilot, but Fresno used to have a population of 440,000 something. So if I tell you the population of Fresno is 440,000, 440,000, does that mean there's exactly 440,000 people? No. These are trailing zeros without a decimal point. So we're going to take the uncertainty to lie in this 10,000 place. And what I'm telling you here is between 430,000 and 450,000. It's an estimate. Okay? Any questions? And then there's something called exact numbers. An exact number you can think of in terms of sig figs having an unlimited number of significant figures. Exact counting of discrete objects. How many fingers am I holding up? 4. So I didn't do 5 because then we could argue about whether your thumb is a finger or not. No. 4 fingers. Is there any uncertainty in that? No, there's exactly 4. So when it's a counting number, it's exact. Now, counting numbers do get a little iffy when you get to really high numbers, and depending on what you're counting, right? Like counting the people in Fresno. The United States does a census every few years. Is that exactly right? No, because in the process of doing the census, it takes some time, and in that span of days or weeks, people die and people are born, and so the numbers change a little bit. So when you get to very large numbers, counting numbers may not be exact. But smaller, discrete objects can be counted. Integral numbers that are part of an equation. The volume of a cube is 4/3 pi r cubed. 4 divided by 3. Those numbers are exact numbers. They have an infinite number of significant figures. And then defined quantities. A foot is defined as 12 inches. It's exactly 12 inches by definition. Now, some conversion factors are defined, others are not. And we're not going to get too hung up on this, but just be aware of that. Let's practice counting sig figs. Okay, so 554 kilometers. How many significant figures? 3. That one's fairly easy. There's 3 non-zero digits. When you see something that ends up being a whole number, like 554, don't automatically assume that it's an exact number. It just happens to be a whole number. There's uncertainty in the ones place for that number. How about 1.01 times 10 to the 5th meters? 3 again. That 0 is trapped between the ones, so it counts. In scientific notation, the decimal part, the part before the times 10 to the something, all of those digits will be significant because the placeholding zeros go away when you put it into scientific notation. Here's the placeholder part times 10 to the 5. This is not counted as a significant figure. How about 1.4500 kilometers? 5. Trailing zeros with a decimal point, those count. 7 pennies. Unlimited, right? So maybe right infinity. 0.00099 seconds. 2. Leading zeros don't count. 21,000 meters. 2. Trailing zeros, no decimal point that's written down, they don't count. Any questions? So when we do calculations, like we did a couple density calculations, and my calculator gave me lots and lots of digits. We don't want to be changing the precision of the result just because we did a calculation. We're not going to gain or lose precision just by multiplying or dividing. And so that's why we have rules for operations. So multiplication and division are related. You could think of them as opposites of each other. So they have the same rule. The result of multiplication or division will have the same number of sig figs as the factor that had the fewest. So if we look at this example, we've got 1.052 times 12.504 times 0.53. And the calculator gives you a result. It's a good idea to just write the whole thing down. But then to figure out what to round it to, we're going to look at each of these numbers and figure out how many sig figs in this one. Well, it's a trap 0. This one has 4. 12.504. All of those are significant. This one has 5. 0.53. Leading 0 doesn't count. This one has 2 sig figs. So that's kind of the hard part. The easy part is, which number is smaller, 4, 5, or 2? 2. That's the kind of question we can handle at 8 o'clock in the morning, right? 2. So that means that we're going to take 6.7208 and round it off to 6.7. We're just going to keep 2 digits. An example of division, 2.0035 divided by 3.20. This is what the calculator says, but we look at our numbers. This one has 5 sig figs, this one has 3, so we can only keep 3 in the answer. So we're going to round it off to 0.626, because that will reflect the actual precision that we have in that result. Any questions? Addition or subtraction. Okay, the rule when you say it in words is a little harder to understand. The result carries the same number of decimal places as the quantity with the fewest decimal places. There's different ways to say that as well. Once you understand it conceptually, it makes a lot of sense. And to do that, it's helpful to pretend that you're going to do this by hand and stack the numbers up like they taught you in elementary school. Line up the decimal points and write the numbers that you're adding. Do the math. Use your calculator. I am not against calculators. Use the calculator so that you get the right answer instead of having a brain fart and adding wrong. And then look at these numbers. Well, where's the last significant figure in 2.345? Well, the 5. One way to do this is to underline. Oftentimes we will underline the estimated digit. 0.07, the estimated digit is the 7. And in 2.9975, the estimated digit is the 5. So then what they've done here is they've drawn a vertical line. They found which one has the greatest uncertainty. Which one has the uncertainty in the largest digit? And draw a line just to the right of that. And that tells you where to round your number. Because what's going on here is we're taking an uncertain 5 and we're adding it to as, well, we really have to start down here. This 5 is estimated. We're adding it to blank and blank. We are so clueless about what those digits are that we didn't even write anything down. So this 5 down here is definitely uncertain. And in this next place, we've got a 5 that has uncertainty, this thing that we know absolutely nothing about, and a 7 that we're sure of. But when we get that result, that's going to be uncertain. In the next place over, we have a 4 that we're certain of, a 7 that has some uncertainty, and a 9 that is certain. So the result of that addition is also uncertain. When we get over here, we have a 3. We're definite on that. This 0, it's not counted as a significant figure, but we know that it's 0. And this 9. And so when we add those up, there's no uncertainty in that result. So here's where our uncertainty lies, and when we record a value, we include the first uncertain digit. So that's how we come to 5.41. Subtracting, we're doing the same thing. So this one ends, there's uncertainty in the 10th place. This one has uncertainty in the 1000th place. The 10th place is a larger amount of uncertainty. So we'll draw a line just to the right of that. We're going to round the number there. Any questions? We'll have lots of questions when we try to do it. That's where you really learn. Rules for rounding. Look at the digit that you're going to cut off. If it's 4 or less, round down. If it's 5 or greater, round up. So let's just go back to this guy real quick. Your book talks about leftmost digit. I think of the first digit that you're going to drop. So I'm going to keep the 5, I'm going to keep the 6, I'm dropping the 7. Then you ask yourself, is 7 5 or greater? Yes, it is. So I round up and I call this 5.7. Over in this one, I'm keeping the 5, the 4, the 1, I'm dropping the 2. I ask myself, is 2 5 or greater? No, it's less than 5. I'm going to round down. So I just cut those guys off and I'm done. What's really important is that the magnitude of the number not change significantly when it's rounded. So if you're rounding to the tens place or higher, you need to be really careful. So what do I mean by that? Let's say my calculator gave me this answer. And I need to round here. That's where the uncertainty is. Is the answer 14 grams? No. I'm keeping the 4, I'm dropping the 3. The 3 is less than 5, so I round down, but I don't round down that much. This is 1,439 grams. I can't round that to 14 grams. That just doesn't work. I need to put placeholder zeros in there. And that's the danger I'm talking about. If you're rounding in the ones place, you're fine. But tens, thousands, no, hundreds. Tens, hundreds, thousands, anything above, sometimes students lose their mind. Okay? So the best thing to do then is to take this number and put it in scientific notation. 1.4394 times 10 to the, I moved that decimal point 1, 2, 3 places. It's a big number, so it's a positive 3. Now if I round, I can do it without worrying about putting in placeholding zeros. So watch out for that. So 4.37, rounding to 2 significant figures, we're keeping the 5 to 3, that rounds up to 5.4. 5.34, 2 sig figs is what we're asked to do. The 4, we're going to just drop. 5.35 rounds to 5.4. 5.349 rounds to 5.3. Sometimes what students do is they'll get a little carried away and they'll start at the end of the number and they'll round back. And they'll say, well, 9 is 5 or greater, so that's going to round the 4 up to a 5. And this 5 is going to round the 3 up to a 4. Don't do that. You'll get the wrong answer about half the time, and you'll do a lot more work. We're going to keep the 3. Keep the 3. We're dropping the 4. You don't need to look at anything else after that. Just look at the first digit that you're dropping. I'm dropping the 4. It's less than 5. 5.3 done. Multi-step calculations. If we have multi-step calculations, which in Chem 1A we do frequently, if you do each step individually and round to the correct number of significant figures, you're going to get some rounding errors by the time you get to your final answer. And so to avoid that, do not round until you get to the final answer, until you're all done. It's always better to write down too many digits because it's easy to cut them off later. If you write down too few and realize, oh, wait a minute, I need more, then you have to go back and do the whole calculation over. So when in doubt, write down extras. If you write down intermediate answers, keep track of the sig figs by underlining the least significant digit. I think that was supposed to be last. I didn't mean to push that. I think it's supposed to be last significant digit. Carry a minimum of 2 extra digits. You can carry 3 or 4 if you want. So in this calculation, do this on your calculator. It's going to show you 19.1707. But here we have multiplication and we have subtraction, and so we need to go back and think about what's going on with the significant figures. Here we have subtraction. This has 2 decimal places. This has 3 decimal places. So the result of that subtraction, which the calculator shows us is 0.479, the last significant digit is the 7. This has 2 places, this has 3. So it should be to 2 decimal places. So I'm going to underline that because this number has 2 significant figures. And then I'm doing multiplication. This one has 3 sig figs. This one has 4. This one has 2. So the 2 limits my answer, and I need to round the 19.1707 to 19. Does that make sense? Do the whole calculation. Write down what your calculator says. Then go back and look at the pieces, especially if you have a combination of multiplication, division with addition, subtraction. If you just have one or the other, it's pretty straightforward. But when they get mixed up, you have to look at it more carefully. So let's do some examples. Do it on your calculator first. So 3.10007 times 9.441 times 0.0301 divided by 2.31. It's a good practice to just write down what your calculator says. Anybody else get that? I sometimes make mistakes. It's really easy to make mistakes when you're doing a calculation on your calculator. So when it's important, like on an exam or finding a result in your lab, do it twice. If you get the same number both times, you probably did it correctly, or you're really lucky in making mistakes. If you get two different answers, go for best 2 out of 3. We have multiplication and division only. So what's the rule for rounding to sig figs? What do we need to look at here? The one with the fewest number of sig figs. So this one has how many? 6. These zeros are trapped, so they count. So that has 6 digits. They're all significant. So this is 6. And the next one is easy. There's no zeros. That one's got 4. How about 0.0301? That has 3. Leading zeros don't count. The trap 0 counts. 2.31 also has 3. The smallest of those is 3, so I need to round this. I'm not going to count that 0 because leading zeros are not significant figures. I'm going to keep the 3, the 8, and the 1. And then I'm going to get rid of the 3. It's less than 5, so I round my answer to 0.381. Always good to write a box or circle around your final answer so we can find it. Let's do this next one. 0.881 plus 132.1 minus 12.02. So calculator says 120.961. Well, we could stack these up, or we could look at them. This is adding and subtracting. It uses the same rule. We're looking at number of decimal places. This one has the uncertainty in the 3rd decimal place. This is in the 1st decimal place. This has uncertainty in the 2nd decimal place. This one has the largest uncertainty. So we're going to round our answer off to 1 decimal place. We're going to keep this. So the next digit is 5 or greater, which rounds the 9 up to a 10, right? So we get 121.0. We need to write the 0 because the uncertainty is in the 10th place. Any questions? So the last two here have mixed. 2.5110 times 21.20 divided by the quantity 44.11 plus 1.223. Okay.
So the 0.881, that would be 3 significant figures, right?
Right. Mm-hmm.
So why wouldn't the 120 be the 3?
That's a good question. This number only has 3 sig figs, and so how can our answer have 4? Because counting the absolute number of significant figures is the rule for multiplying and dividing. The rule for adding and subtracting is a little different. We're looking at decimal places. Okay? And that's what trips people up with the adding, subtracting thing. Yeah, very good question. Yeah, you can have, funny things can happen when you're adding and subtracting. You can end up with a number that has way more sig figs than any of the numbers that were involved in it. And you're like, whoa, what happened? But it has to do with where the uncertainty is. So with this one, letter C, my calculator is showing me 1.17427 0.0399. Well, we've got adding mixed with multiplying and dividing. The rule for multiplying and dividing is we'll look at the number of sig figs. So that first one has 5, and this one has 4. And then we're dividing by this quantity. We have to look at the result of that. So sometimes that involves going back and doing part of the question again. When we add those together, this part here is 45.333. We have to use the adding rule. So 2 decimal places, 3 decimal places. So this gets rounded to, 2 decimal places. That number has 4 sig figs then. So this has 4 sig figs, 5, 4, and 4. So this should have 4 sig figs. So we're going to keep 1, 2, 3, 4. We're going to keep up to here. And so we're going to say this is 1.174. Any questions? I'm going to erase this. Yeah, that's not erasing, is it? Erase that because it's in my way. Let's look at this last one. 12.01 times 0.3 plus 4.811. Calculator says 8.414. It's tempting to look at these and say, oh, well, this one only has 1 sig fig. I round the answer to 1 sig fig. Don't do it. There's adding in here. So what we need to do is we need to look at the result of this and see how many sig figs that has and where the decimal places are, and then compare it to this. So the result of 12.01 times 0.3 is 3.603. Multiplication, 4 sig figs, 1 sig fig. So this only has 1 significant figure. I'm not going to round it off to 4, though, when I do the calculation. I want to keep the whole number, and I'm going to round at the end. So now I see that this has 1 decimal place, and this has, I'm sorry, this isn't even a decimal places. This is in the ones place is where the uncertainty is, and this has the uncertainty over in the 3rd decimal place. Let's stack these up so we can see it a little better. The uncertain digit, no, that's not what I wanted to do. We're not adding the 8, we're adding the 4. 4.811, the uncertain digit, is over here. So if we're doing a line, we're going to draw it to the right of the first uncertain digit that we come to, which is in the ones place. So this does get rounded to 8. But not because there's 1 sig fig necessarily. So be careful with your mixed calculations. Any questions? Precision and accuracy. Accuracy refers to how close the measured value is to the actual value. How close to the bullseye did you get? Precision refers to how reproducible it is. So maybe you're playing darts and you hit to the left of the dartboard. You're not even hitting the board. Your accuracy sucks. But you throw 10 darts and they're all within a centimeter of each other over on the wall. So your accuracy is terrible, but your precision is great. accuracy and precision can both be high, they can both be low, or one can be high and the other can be low. Let's look at some results of a student experiment. 3 students took a lead block that was known to have a true mass of 10.00 grams, and they weighed them. Each student weighed the block 4 times. And these are their results. So, student A, the first time it was 10.49, 9.79, 9.92, 10.31, and then they get an average. And student B and student C. And what's happening here is not that the block of lead is changing mass, but the students aren't very good at weighing it, so that there's error in their results. It's a little hard to look at this table and figure out exactly what's going on. And this is why we often graph things, because it brings it out more visually. So here's student A. And here we have his first trial. It was almost 10.5 grams. And his second trial, his third, and his fourth. And so we see that here is the true value. And his values are all over the place. This one's really high. That one's really low. So this is not precise, because his 4 results here vary widely. And his average isn't great either. It's above the true value by a significant amount. So this is inaccurate and imprecise. This student, see how the bars here are close together? They're all about the same. That's good precision. But his average, represented by the red dashed line, is below the true value. So he's precise but inaccurate. The third student, values all agree, they're close together, and the average is very close to the true value. So this is accurate and precise. We would always like to be accurate and precise. One of the reasons that we often repeat measurements is because there can be random errors. There are random errors. They're unavoidable. Random errors mean sometimes it's high, sometimes it's low. The thing about random errors is when you average the results, the highs and the lows cancel each other out, and so you can get rid of random error by repeating measurements. And so you'll see that we'll often do experiments, we'll do 3 or 4 trials so that we have some numbers we can average. It also helps you to see how your precision is. Usually, if you have poor precision, you really have to wonder about your accuracy. If the precision is good, it's a good sign, although as we see here, it doesn't guarantee that you're accurate. But we're going for both. So random error, equal probability of being high or low. You can get rid of that by averaging. Systematic error is an error that tends to be in the same direction, either always too high or always too low. If you're reading the top of the meniscus instead of the bottom of the meniscus, all of your volumes are going to come out a little high. If you're weighing something on the balance and you're sticking your thumb on the pan, right? Hopefully, this is really dumb, but if you stick your thumb on the pan, then the mass is always going to come out high. That's a systematic error. So we try to get rid of systematic errors by using good technique, and we try to get rid of random errors by doing multiple measurements.